Okay, in this lecture we want to talk about Bessel's equation and Bessel functions. Now, you can spend a lot of time on Bessel's equation, or you can spend just a little time on Bessel's equation. This semester, we're not going to spend a lot of time on Bessel's equation. We're just going to show it and show the basic solution because it's an example of an equation that we solve with the method of Frobenius. So you can see we have this x squared y double prime, we have xy prime, and then we have this function of x times y, and this nu is kind of analogous to Laplace's equation. It's an index that's going to define the type of physical problem that we're solving, which kind of determines the type of solutions. The most common application of Bessel's equation is in problems that have a cylindrical geometry. If you have had an electromagnetic fields course, you know that when you have cylindrical waveguides or even like cylindrical conductors, the solutions to field distributions in those are Bessel functions. So in standard form, this is what Bessel's equation looks like. And according to the method of Frobenius, this does have a solution where we have this series solution multiplied by x to the r. And in this case, my equation, we've already taken the x to the r and moved it inside the summation sign. So we're making an assumption we have this for our solution. We would follow our standard approach where we would take the derivatives of that along with the actual equation coefficients, substitute everything into the differential equation. Because, let's go back just a little bit. If we look here, this is already written as a polynomial. So I actually, on these terms, am not going to need to do a series expansion because it's already, basically, it's already a polynomial. So if I look at this and collect the lowest power of x, then I get the following indicial equation where r plus nu times r minus nu is 0, which gives me roots at plus and minus nu. Those are two distinct roots, so I get a recursion relationship when I equate coefficients. And once again, notice that while m runs in integer units, the coefficients will only give me only get every other coefficient. So I've got a to the 2m and a sub 0. So that's my recursion relationship. If n is not an integer, or if it's an integer, so what this depends on is whether or not nu is an integer. So if nu is an integer, then we get the nth order Bessel function. And here's an example of n equals 0 and n equals 1. And so that would be when nu was an integer. So you can get the 0th function or j sub 1, the first order. So you're getting the nth order Bessel function. What these look like, they look like this. One of the things that's different in the Bessel function and the Legendre function is the Bessel function isn't, notice it could be 0 at 0. In fact, all of the higher order Bessel terms are 0 at 0. And so if you were looking at fields inside of a cylindrical waveguide or fields maybe due to a cylindrical current or charge distribution or a cylindrical antenna, an antenna with cylindrical geometry, you'd see this kind of a distribution for a field pattern, just depending on what your boundary conditions were. So the Bessel functions are interesting functions. They do describe cylindrical geometries very well. In this particular semester, we're not going to go through the Bessel functions in great detail other than just to show them as we've done in this lecture.